Welcome to Empowered Learning. This video will be a summary of the various types of limits that we see in a first year calculus course, and to also see how we actually interpret those limits as properties on the graph of a function. So I'm making this video so that whenever we go through the whole notion of trying to figure out how to evaluate the limit of a function, whether we're looking at a graph of a function, or more so whenever we're only given the algebraic representation of a function and we're actually evaluating the limit of it as we approach a particular x value, or as x approaches positive or negative infinity. A lot of times we get the whole concept of what it is that we're actually asking for whenever we say evaluate the limit. Sometimes we lose the whole notion or concept of what that actually means. So I wanted to make this video so that it's clear to you that when we evaluate the limit of a function, what we're really doing is translating into another language, meaning the language of calculus, the same things that you learned when you learned about graphs of functions in a college algebra or a pre-calculus course, okay? So we're going to look at these one by one and see, hey, how does a limit along with something else that we may know about the function sort of work together to tell us in this new language of calculus what that actually means about the actual graph of the function. So we see here, if we know that the limit of some function f of x as x approaches a from both the left and the right side equals some real number L, and that's why I have this here. And on top of that, we know that we have a point AL on the graph, meaning that the y coordinate for the point on the graph when x is equal to a is the same y value that L is. Then what that tells us is that our function is continuous at x equals a. So that means whatever's going on with that graph, we may not know much about f of x in this graph, but we do know that at x equals a is going to be continuous. And by definition, what that also means is that our function is going to be defined at x equals a, okay? And that's what that actually means. And with it being defined, it will actually be defined at the point AL, okay? So whenever we have questions or anything that we're dealing with a function, and we're given information about the limit of the function equals some real number, and we know what that point is on the graph of that particular function, and these numbers match, then we know that that function is going to be continuous there. Now, if we contrast that with this next limit, here we see that the limit of f of x as x approaches a from both the left and the right equals the same real number L, but now we see that the function is, the y value of the function when x is a is not equal to the same thing that the limit is. In that case, what that communicates to us is that we have a jump discontinuity, okay? So notice that if f of a was equal to L, this point now would actually be down here, and it would be filled in like this, and it would be called continuous, okay, at that particular x value. But because of the fact that we have fact that it looks like this, and we know that our function does not have the same y value as x equals a as the limit of the function, then we know we have this specific type of jump discontinuity, okay? All right, so moving on to the next limit, we see that if we have the case where the limit of the function of f as x approaches a from both the left and the right exists, but the function is undefined at x equals a altogether, then what we have is a hole in our graph, okay? And so if you've watched the videos that I've made on limits, whether it's the primer on limits, the one where we were looking at the limit laws and we were evaluating limits algebraically, that first video, the second video that I made on evaluating more limits, and we talked about the conjugate radical techniques and other techniques or tidbits and tips that we could use. in all those videos, one of the things that I mentioned here is we need to take into account for what the limits actually mean. And in specific cases, when we had like 0 over 0 or infinity over infinity as the indeterminate forms that we came up with, if we just plug numbers into it, one of the things I told you is that whenever we have that situation, we normally end up having a hole in the graph. So for all those examples that I did in those videos to where we would end up getting 0 over 0 or infinity over infinity, specifically 0 over 0, we would have a situation here where we actually end up having a hole in the graph. So whenever you know that the limit of your function at a particular x value exists, but the function's actually not defined at that particular x value, then you know you have a hole in your graph. All right, so the next set of examples that I have here are to sort of showcase what it looks like from a limit perspective whenever we have vertical asymptotes. Now, in the video that I did on one-sided limits and infinite limits, I did start to talk about the whole notion of limits and how they look when we say, all right, we have a vertical asymptote in the graph of this function. How is it going to look in terms of limits? So what I'm doing different here is I'm actually giving you all the scenarios, but also giving you graphical examples of that. So here we see that if the limit of our function here as x approaches a from both the left and the right, so without the plus or the minus like how you see here, if we have this situation, then we're looking at the behavior both on the left and right side of x equals a. If we answer with positive infinity, the graph looks like this. So the graph has to go up towards infinity on both sides of x equals a. If we answer with negative infinity, then the graph has to look like this one. Okay. If we talk about only the limit of the function as x approaches a from the right, if we have to answer with positive infinity, then the graph looks like this. So as you can see, the graph is going upward as x gets closer to a. And if we answer with negative infinity, then the graph is going downward as x gets closer to a. And let me erase that because I kind of crossed over the vertical asymptote there and I shouldn't have. So it's more like this, okay? And of course, if we're only looking at it from the behavior of this function on the left side of x equals a, if we answer with negative infinity, graph goes down like this. If we answer with positive infinity, graph goes up like this, okay? And so these are all 6 cases here, but we do have to pay attention because what's being communicated is different if we have just x approaches a versus having x approaches a from the right versus having x approaches a from the left. So we do have to pay attention to that. And in particular for these cases here, we're describing one side of the vertical asymptote, whereas here we're saying that both sides of the vertical asymptote, well, the function on both sides of the vertical asymptote are going to act the same. All right, so the next examples that I have here are how we express that we have a horizontal asymptote on our graph. Okay, and remember, horizontal asymptote is just a special type of in behavior. Okay, and in behavior just means as x approaches positive infinity or negative infinity, what is my graph going to act like? So in the case where the limit of the function as x approaches positive infinity is going towards a particular real number, then that means it's approaching a horizontal line. And in this case here, this is what it looks like when x approaches positive infinity, here and here. And of course, this particular function also kind of displays what happens when x approaches negative infinity as well. Now, the point I want to get across here is that we can have functions that have a horizontal asymptote as x approaches positive infinity, but not when x approaches negative infinity. And so this particular graph here is an example of that. And it can be vice versa as well. We can have functions to where we have horizontal asymptote as x approaches negative infinity, but not have that sort of thing happen as x approaches positive infinity. Okay. The last set of examples that I have here are to describe all other types of in behavior. And so I say it that way because in general, let's say if x is approaching positive infinity, most functions are going to have one of three types of in behavior. Either going to go up to positive infinity, go down to negative infinity, or they're going to ride along a smooth horizontal line. Okay. And they'll get closer and closer to this line as x gets closer and closer to infinity. And so we want to make sure that we take into account of that. Of course, we've already taken into account of the horizontal asymptote case. Now what we're doing is take into account of these other cases here. So if the limit of our function as x approaches infinity is infinity, that just basically means that we have a situation like this. As we take the limit as x approaches positive infinity and we end up with negative infinity, then graph looks like this. And of course, limit of function as x approaches negative infinity and we get positive infinity, looks like this. And then lastly, if we take the limit of the function as x approaches negative infinity and we get negative infinity, graph's going to look like that. And that's just for that piece of the graph. Okay. Now, the purpose of going through all of this is to say, now that we understand what limits are, which is our fancy way in the language of calculus to be able to describe the behavior of a function, and we've also at this point, we should know what the definition of continuity is in terms of limits. What we really use all this for is to be able to say, well, hey, I want a function that has these properties. Okay, can you draw me a function that has all these properties in it? And what we're going to do is express the properties that we want in a particular function by either using limits and or other things that we know from pre-calc. And so I'm going to do an example of that to kind of show you how we can actually use these concepts to be able to piece together what the graph of a possible function would look like given we get its properties. So for this example, we're asked to sketch a graph of an example of a function that satisfies all of the given conditions. Okay. Now, I want to focus that I want to sketch of an example, meaning one function that satisfies all of these properties, or all of these conditions here. The reason why I'm stressing that is because my experience has been when students first try to take on this concept here, they think that they have to draw a graph of a function that just satisfies this one, and then a graph of a different function that satisfies this one, and then a graph of a different function that satisfies this one. And if we keep on doing that, you'll see that we'll have 7 different functions on the same graph to try to satisfy all these conditions here. And that's not what this particular problem is asking for. Okay. We need the same function to have all of these properties at the same time. If we made the mistake of drawing 7 different functions to try to meet all these properties, more than likely what we're going to end up with is a drawing that doesn't satisfy the definition of a function in the first place, meaning that it won't pass the vertical line test. And so I want to make sure that you don't make that mistake before we even get started. So I don't even want you to be thinking in that realm. Okay. All right. So now that we understand that the graph that we're going to have is going to be one function that's going to satisfy all these conditions, what we need to do is identify what are these conditions or these properties actually communicating to us. Okay. All right. So we're going to start with the first one. So here, what we're told is that we have the limit of this function as x approaches 2, and it goes to negative infinity. If you remember, here we have a limit of a function that approaches a specific x value, and it ends up being positive or negative infinity. If we go back to what we studied here, we see that that kind of thing happened whenever we were talking about vertical asymptotes. Okay. And so here, specifically speaking, it would be this example here. So either the graph is going to go up or down depending upon what information is given. And so here, what it's telling us is that we have a vertical asymptote at x equals 2. Okay. And to be specific about it, is the behavior of this function around the vertical asymptote is going to be the same on both the left and the right. So if I was to try to draw a quick graph of it, function is going to look something like this around that vertical asymptote. Okay. So that's what property A is telling us. If we look at property B, it's telling us the behavior of this function as x approaches negative infinity is going to 0, meaning it's going to a real number. If we go back and look here, limit of a function as x approaches negative infinity equals a real number, that is a horizontal asymptote. Okay? So what this example is telling us here is that we have a horizontal asymptote at y equals 0. Okay, and of course y equals 0. This is better known as the x-axis. So as of right now, our graph has a vertical asymptote at x equals 2, where it's going to look like this, and we also have a horizontal asymptote at y equals 0. So since we have this, I'm going to go ahead and draw this into our graph that we have below so that we can kind of keep up with everything as we go along. So here's our Cartesian plane, and I'm going to draw me to the best of my ability here. I'm going to try to do vertical asymptote here at x equals 2. Oh, got a little unsteady there. All right, so let's, slowing up on me, so that's why it's doing that. All right, so let me try to make the dots a little slower so the computer catches up with me. All right, that's good enough. All right, so we have x equals 2 here. And we also have a horizontal asymptote here on the x-axis. And our function, I'm going to draw this in a different color here. Let's do it in, we'll do it in green. We know that the function is going to look like that on either side of the vertical asymptote. And we know here that we're going to have our function, and I think this is as x approaches negative infinity here, is going to approach this graph. So we don't know if it's going to come from up here or down here. We don't know. So we'll just draw both, and then once we're done, we'll make a decision on which one it should be. All right, so let's go back up and let's look at the next thing that we're given. And so we see here, we're also told that the limit of f of x as x approaches infinity is infinity. Okay. Now, if you look at this, this was one of those in behaviors here. And to be specific, is this one. So this in behavior means that on the upper right-hand part of our graph, as x approaches infinity, y is going to go to infinity. Okay. So here, this just essentially says here that we have in behavior where the graph's going to go up like that. Okay. So we're going to go down here and make note of that as well. So here, as x approaches positive infinity, graph's going to go up like this. Okay. All right, so let's look at what we have next here. So we see here we have the limit of a function as x approaches 0 from the right is infinity. So anytime we have a limit of a function going to a specific x value being infinity, just like how we had here, we have a vertical asymptote. But notice that we only know what the right-hand side of that vertical asymptote looks like, okay? If we look at E, we see that we have same thing, but now we're also looking at the left side, okay? So for that reason, these two limits are actually working together, okay? And these two limits are working together to say, yes, we have a vertical asymptote at x equals 0. And the way that this particular function is going to look around that vertical asymptote is, if this is my vertical asymptote at x equals 0, I know that to the right of it, the graph of the function is going to go up to positive infinity, and to the left of it, it's going to go down to negative infinity, okay? So it's going to, look opposite on go down one way, go up another. So let's go ahead and notate that on our graph as well. So here we have another, I'll just try to do the best I can to make another vertical asymptote here at x equals 0. And for our function, let's get the right color here. On the left side, it's going to go down to negative infinity like this. On the right side, it's going to go up to positive infinity like that. Okay. All right, so now for our last two, f and g, notice that we say that f of 4 is undefined. So that lets us know that when x is 4, it doesn't have a corresponding y value, but we don't know what exactly is going to be there. We don't know if it's going to be a vertical asymptote, if it's going to be a hole, if there's going to be a gap, we don't know. But if we look at f and g together, we see that the limit of this function as x approaches 4 from both the left and the right exists because it's actually equal to a real number, but the function itself is not defined there at x equals 4. So if we go back to what we saw here, here's a situation where the function is not defined, the function is not defined at all at x equals some value, but the limit exists. We know that that tells us we have a hole in our graph at, in this case, x equals 4. So here we could use what we know for g and f to basically say that we have a hole in our graph, and the location of that hole is going to be at the point 4, 6. And we know that because we're approaching an x value of 4, corresponding y coordinate that the function acts like it's going to is 6, even though when we get to 4, there's nothing there. So here, if we come down to our graph, we can actually put a hole in the graph at the point 4, 6. So go 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6. So we would have a hole in our graph right there. Okay. Now, based upon what we see here, notice that we have everything that we need to be able to draw the graph of this function. Now, I know we needed to make a decision upon whether we want to keep the whole thing with the horizontal asymptote at y equals 0 as x approaches negative infinity being up or down. Since we weren't given any other information to let us know, we could choose either one of these, okay? And depending upon how you want to draw this function, depends upon whether you want to keep this one or keep this one, but you can't have them both, okay? So for just illustrative purposes here, I am going to erase this one, okay? Now that we have all the properties in place here, I could come up with a graph of my function, and it doesn't matter what I come up with as long as that function meets these properties here, okay? And so I'm going to change colors here and try to draw an example of what I mean. So I'm going to draw this in red. So what I know is that this function here, just looking from the left, going to the right, is going to have to ride along this particular, right along the x-axis here. And eventually from here, it's going to have to get back down here. So what I could do is say my function is going to act like this, but then it may come like this and then come down like that, okay? Now, here, I notice that for this particular function at x equals 0, if this goes down, this has to be up like this. And of course, at x equals 2, on the left-hand side, this has to be down. So this function could do something like this, okay? And then, of course, for here, notice how this has to be down as well. So this could be down, and this could come up here and connect with this hole. And then after that, the function could kind of dip down like this if it wanted, and then come back up here. Really doesn't matter. I could have kept it like this and just connected it straight there. So the point I'm trying to make here is that this is just one of many examples of what I could come up with as far as the graph of a function that would satisfy all the conditions that I have talked about up here, okay? The only thing that matters is that whenever you do problems like this is that, number one, the graph that you have represents a function, which means that it passes the vertical line test. And number two, that it satisfies all these properties. And if you look, my graph does do just that, okay? My graph does pass the vertical line test everywhere where you look. My graph also satisfies all the properties that we had. So we had the property of having the horizontal asymptote at y equals 0 as x approaches negative infinity. Of course, we had x equals 0 vertical asymptotes, and the function kind of flip-flop on either side. At x equals 2, another vertical asymptote. The function had the same behavior on either side. We had a hole in the graph at 0.46, and our end behavior as x approaches positive infinity also went up to infinity. And so again, you could erase this and draw a graph that looks totally different than what I have. But as long as it satisfies those same properties, your graph will still be correct, okay? All right, so I hope that this example sort of explains one of the reasons out of many why we study limits and why we want to be able to interpret limits in terms of the properties that are on the graph of a particular function. All right, take care.